Hello everyone and welcome to Make Learn 360. So in this video I want to solve some couple of questions with you to illustrate the concept of um, deflection and axial loading. All right, so let's solve this problem together. Now we have so let's read it. Both portions of the rod ABC are made of an aluminium for which E is 70 gigapascal. So basically, E for aluminium we know as 70 gigapascal. Now, knowing that the magnitude of P, so for the first part of the problem, P is 4 kilonewton, and that determine the value of KO, so we don't know. So that the deflection at A will be 0. So in other words, what is the value of KO here? So that the total deflection at A is 0. That is the question. And then the corresponding deflection at B. All right. So what we are trying to say is that there is going to be deflection at A, and then there is also going to be deflection at B. But then the question is saying that we should find the value of KO so that the deflection at A will be 0. Okay. And then find the deflection, the corresponding deflection at B. So how can I solve this problem? Now the first thing we want to do here is to calculate the areas. Okay, so let's find the areas. So the area of AB, we know that the diameter is given as 20 mm. So this is what I'm talking about. The diameter of AB. Okay, so let's go ahead and find the area. So area of AB is pi times the diameter, which is 20 squared over 4. And this gives us what? All right, so pi multiplied by 20 squared divided by 4. And that gives us 314.159. So let's say 314.16. 314.16 millimeter squared. And then let's calculate the area of BC. So the area of BC is pi. So the diameter is 60 squared over 4. So I'll just go ahead and change the 20 and make it 60. So what do we get? 2827.43. 2827.43 millimeter squared. So basically that is the area of BC. Okay, now we know the areas and then the force. So for the first part we are assuming that Q will be 0. Okay, now let's look at it this way. The force in member AB is what? A tensile force. And then so this is what we are saying. The force in this member is a tensile force because of this P. And now looking at it carefully, we can say that the deflection is going to be P multiplied by L A E. Okay, so let's solve for the deflection. Now the deflection will be the load, which we know as P, giving us 4 kilonewton. So okay, this is what I'm trying to say. P is 4 kilonewton. So 4 times 10 to the power 3, and the length of P is 0.4 meters, which is the same as 0.4 times 10 to the power 3 millimeters. Then I will divide here by the area, which is 314.16 millimeter squared, and then E. So E is 70 gigapascal. So if I want to convert 70 gigapascal to megapascal, that will be 70 times 10 to the power 3 megapascal. Why are we doing all this? We know that Newton per millimeter squared is exactly a megapascal. All right. So 70 times 10 to the power 3. So that the final answer that we will get will already be in, millimeters. Okay. So it's going to be 4 times 10 to the power 3 multiplied by 0.4 times 10 to the power 3 divided by 314.16 multiplied by 70 times 10 to the power 3. Okay, now what we have here, okay, so our deflection will be 0.073. So 0.073 millimeters. That is the sort of the deflection in this rod. Okay, now so let's look at this carefully. In BC, what will be the force in BC? So the force in member BC will actually be all right. So so now let's do something here. We've been able to find the deflection in AB. Let's try to find the deflection in BC. Okay, let's try and find the deflection in BC. So now the deflection in BC will be okay, so this one is AB. So for the deflection in BC, it's going to be the load PL over AE. But the P here, so everything has to do with BC. Now the question is, what is the force in member BC? If you look at this critically, what do you see? At A, the load is P. At B, the load is what? Q. Okay. Now, if I take member BC here, what will happen? What is the load that will be within this? Now, the load which is within this is nothing but is going to be in compression. Okay. Because of this force acting on it, is going to be in compression. But instead of it to be P minus Q, it's going to be, okay, you can say that P minus Q and then you can negate it. Okay, why P minus Q? Because this force here will be felt throughout. This load here, P, will be felt throughout here. And then this load, Q, will be felt throughout here. So the net force within BC is not only Q. I hope the concept is clear. The net force within BC is the effect of P and then Q. But this sort of force is compressive, and then it is given by the net effect of P minus Q. But it's a compressive force. So in fact, it is going to be Q minus P. Okay. Because that will be like compressive force. Okay. So then here will be Q minus P. That is the force within BC. However, the length of BC is still the length, which is 0.5 meters. The same as 0.5 times 10 to the power 3. Then you divide this by the area, which we solved already. For BC, the area is 2827.43. 2827.43. And then the Young's modulus don't forget that um, it is still the aluminum. So 70 times 10 to the power 3, so that we can convert the mega to the gigapascal to the megapascal. Now at this juncture, I want you to be very careful here, because from the question, he said that the deflection, if the deflection at A is 0, that is the first part of the question. If the deflection at A here, if the deflection here is 0, then it means that there was no net deflection. Therefore, the deflection which was here was the same as the deflection which was here. Okay, think about it this way. The total deflection at A will be the deflection of AB plus the deflection of BC. But if there was no deflection at A, which is 0, then it means the deflection here will be the same as the deflection here. The only difference is that this one was sort of tension or a tensile force. This one would be compressive. All right. So based on that argument, we can say that our load, we can say that our deflection in AB will be the same as deflection of BC for deflection at A to be 0. And that is the reason why I told you earlier on that P minus Q is what we are supposed to get. But because of the fact that this will undergo compressive, that is why we are negating it. All right. So at the end of the day, it's just going to be Q minus P. All right. So from here, we can say that deflection of BC, which is Q minus P, multiplied by 0.5 times 10 to the power 3, or divided by 2827.43 multiplied by 70 by 10 to the power 3 will be the same as 0.073. From here, if we solve for Ko minus P will be what? 0.073 multiplied by 2827.43, 70 multiplied by 10 to the power 3. Then I will divide the whole of this by 0.5, 10 to the power 3. So Ko minus P will be what? So Ko minus P, so let's punch it on the calculator. So Ko minus P will be given by 0.073 multiplied by 2827.43 multiplied by 7 times 10 to the power 3 divided by 0.5 times 10 to the power 3. And what is that? So we are going to get 28,000. So 28896.33. So this value that we have gotten here is some sort of in terms of how do I put it? It's actually in terms of newtons. Okay, so in terms of newtons. All right, but what can we say? So all right, so we equated the deflection here to this deflection, right? And then what we are actually solving for, this Q minus P here is some sort of force. So in fact, it means that Q minus P will be 28.89. So let's say um 28.90 kilonewton. Okay, so that is what we are getting. So it means that if we want to solve for K, that is what the question said. K will be 288. Okay, let's just write it straightforward. 28.90 plus P, but P is 4, so it's going to be plus 4. P is 4. P is 4 kilonewton. So that is K. K will be so 28.90 plus 4. And what is it? 32.90 kilonewtons. All right, so there we are with K. But let's look at the second part. So the second part of the question said that the corresponding deflection at B. Okay, so if we want to calculate for the corresponding deflection at B, we know that for the deflection at B, what is it going to be? All right, so it is interesting to know that the deflection at B will be the same as so think about it this way. There is no deflection here, so it means that the deflection within this must be the same as the deflection within this. So the B will receive the same deflection. Okay, so point B will receive the same deflection, which we have already calculated as 0.073 millimeters. That's all. So now, in fact, we are done with the first part of the problem. Let's come to the second part of the problem. It says that this time round, the same question but different preamble. This time round, he says that the rod ABC is made of aluminum, the same thing. E is 70, the same thing. Now you know P and now you know Q. So find the deflection at point A and then B. So this for this problem, you know P and then you know Q. So let's see how we can do this. Okay, so maybe let me copy the question again here. All right, so for the second part, P is 6 kilonewton, Q is 42 kilonewton. All right, now so the same thing, E is 70 gigapascal. Find the deflection at point A and B. So E is 70 times 10 to the power 3 megapascal. We are to find the deflection at A and then point B. So for this problem, it's going to be straightforward because we know the values. So I'm not going to do anything again because we know everything. So the area of BC is giving us what? Area of AB is 314.16. So 314.16 millimeters squared, and then area of BC is 2827 so 2827.43 millimeters. So now we know the area of AB and then BC. Now let's move straight forward. Interestingly, we know that what P is 6. So without wasting much time, the deflection through AB, let's calculate that. By the way, the deflection at A this time is not 0. So it's going to be the deflection in AB plus the deflection in BC. Think about it this way. There is going to be deflection here. So it is going to be the deflection within this plus the deflection within this. And that will add up to get the total deflection at A. Okay, so it means we need this and then we also need this one. All right. So now let's first of all calculate the deflection within AB. So it's going to be 6, P. Okay, let me write it again. P over PL over AE, which is 6 times 10 to the power 3. And the length is 0.4 times 10 to the power 3 in millimeters, divided by the area, which is 314.16, multiplied by the Young's modulus in megapascal. So the deflection in AB when P is 6 will be 6 times 10 raised to the power 3 multiplied by 0.4 times 10 raised to the power 3, 314.16 multiplied by 70 times 10 raised to the power 3. And that gives us 0.109 meters millimeters, sorry, 0.109 millimeters. Let's do the same thing for BC. So for BC, what do you think will happen? For BC, if we want to get the load, what do you think will happen? The load in BC. So to get the load in BC, we can make a section here, and it's going to be something like this. So P is here, this is B, and then there is Q here, and then I have taken a section here. So if I take a section, then I have PBC. So PBC is coming this way. So this is some sort of free body diagram. So if I sum forces, or in other words, for the purpose of equilibrium, then PBC must be what? Okay, let's do it this way. I want you to familiarize with this. So P is going up, and it should be equal to Q plus PBC, which are coming down. So what is PBC? PBC will be what? P minus Q. Okay. So for this one, PBC is what? P minus Q. All right. Don't be confused by this when you realize that in the first one we did it Q minus P. Don't be confused about this. Okay. Because with the first one, the deflection at A was 0. Okay. Now, so what this is telling us is that if we want PBC, it is going to be P minus Q. So therefore, it's going to be 6 minus 42. Okay. All right, so PBC 6 minus 42 multiplied by L. So the L is the length, which is what? 0.5 times 10 to the power 3 divided by the area. And what is the area? We have it already. 27.43. All right. In fact, we need to multiply the load by 10 to the power 3. And the length is 0.5 times 10 to the power 3 in millimeters. Area and then the Young's modulus. All right. So in other words, the deflection in BC is going to be 6 minus 42 times 10 raised to the power 3 multiplied by 0.5 times 10 raised to the power 3 and then divided by 2827.43 multiplied by 70 times 10 raised to the power 3. So you see we are getting negative, so minus 0.09. So the negative results is as the fact that we are actually getting, a compressive force on BC, which is true. Okay, so all right, that is it in terms of millimeters. All right, so then the deflection at A, so we have this and then we have this. So this one will be 0.109 minus, because it's supposed to be plus, but then it is minus, so we just negate it. So what is it, the difference? 0.109 minus 0.09. So 0.019 millimeters. So this is the deflection that we will see at A. All right. Now we are not done. The question said we should also find the deflection at B. So you see, find the deflection at point A and then point B. So let's move ahead and find the deflection at point B. So for the deflection at point B, it is basically the same as the deflection through BC. All right. Why is it so? So we are saying that the deflection at B is the same as the deflection at BC. Because in fact, if you take the BC is the whole of this. So the deflection which is experienced within here must be the same as the deflection at this point. In other words, if this BC expands or whatever it is, that deflection will be this deflection here. Okay. Now, at this juncture, it means that the deflection here is minus what? 0.09 millimeters. All right. So it means we are done with the problem. But then the negative sign means that it will go down instead of going up. It means that the deflection will go down. Don't forget that this force, this member is actually receiving some sort of compressive stress, and that is why it's going to come down. All right. So thank you very much for watching.